Welcome everybody to Conquer AI Performance, Cost and Scale with AWS AI chips. My name is Gadi Hoot. I run Product and Customer Engineering at AWS Annapurna Labs. And with me we have three amazing speakers, Yang from the Amazon Rufus team, Joe from the Poolside team, and Matt from Google DeepMind. We are all here to cover the latest announcements on Trainium 2 and give you updates on Trainium and Inferentia in general. We have a lot to talk about. Let's get started. I guess we are all here because we have some interest in AI and Gen AI specifically as a technology and how it enables innovation. Like Matt, our CEO, says, the job here at AWS is for us to enable customers to have access to this amazing technology as securely, performantly, and scalably possible. What it means for us, the team at Annapurna Labs that build the chips, the boards, and the software around them, is we need to keep innovating on your behalf to make sure we can deliver the scale and the performance you guys all expect. We started this journey back in 2016. Literally a few engineers in a room trying to figure out how to build ML systems that are high performance and cost effective. This has been the leading tenet for us ever since, providing the performance at a reasonable cost. And we delivered the first instances, Inf1, that had 16 Inferentia 1 chips back in 2019. And we've been delivering ever since. And of course, the latest announcement this morning, Trainium 2 in general availability with the Tier 2 instances and the preview of the Tier 2 Ultra server. Before we dive into the technology, I want to explain why we keep building systems that are larger, more performant. I think most of you have probably seen this graph before. Basically, what it shows is that over the last decade or so, models have been growing at an exponential rate. Now, the question we need to ask ourselves, why is this happening? Well, the answer is pretty straightforward. Research behind it is not that straightforward, but research shows clear evidence that with model size growing, the accuracy and the performance of the model improves. What you see here, these graphs are from a famous paper back in 2020, the scaling laws of neural language models. And the study shows that performance improved predictably as long as the compute, the data, the training data, and the model size itself grow at a similar rate. Let's zoom into the performance aspect because that impacts the infrastructure. What you see here is something very interesting. This is a log-on-log graph. What it means is that the straight line you see here, intuitively, you would think it's addition patterns, but it's actually a multiplication pattern. So if a data scientist wants to improve their baseline model by 50%, they have to invest 10,000x more compute in order to reach that result. 10,000x. What it means for us when we build those systems, we of course need to keep improving performance, but we have to keep power at bay. If we won't do that, we won't be able to scale to your needs. So what does it mean for us for future models? The trends we see from customers are very clear. The model sizes will continue to grow, and therefore we need to keep up. And this is where Trainium 2 comes for the rescue. Trainium 2 is our most complex chip we designed to date. It packs 1.3 petaflops of dense compute. Just to give you a reference, the first instance we launched only 5 years ago, a single chip of Trainium 2 has 30% more compute than that entire server. And we also added innovation here. For example, we are the only solution in the industry that provides 4x sparsity, which means that if your model is sparse, you can get up to 4x boost in your compute, available compute. Let's look at how this all looks inside the server. This is the Trainium 2 server. It packs a whopping 20.8 petaflops of compute, 46 terabytes per second of HBM bandwidth, 1.5 terabytes of HBM memory. What it means as compared to other options on AWS? Simply put, Tier 2 has 30% more compute than the latest GPU instance, the P5en. Compute is very important for training and inference, but also HBM. HBM memory has to keep up, because it has a dramatic impact on the model performance. So also on HBM, we have 30% more HBM than is available on the P5ens. And of course, we are building those in the largest ultra clusters we've built to date. Let's look at performance. These are results that were verified by artificial analysis. It's an independent benchmarking site. And you can see here that Trainium 2, on the y-axis you see latency or time to first token. On the x-axis you see throughput or output speed. And you can see that Trainium 2 is more than 3x the throughput of the next available solution from cloud providers. Another great example is coming from Anthropic. What you see here are results, again, verified by artificial analysis, of the Haiku 3.5 model. Compared to TRN1, TRN2 is 60% more performant. Compared to the other cloud provider that is deploying Haiku 3.5, the result is 41% faster. Truly amazing performance. With performance in mind, I want to hand it over to Yang from the Rufus team to tell you how Amazon Rufus scaled with Inferentia and Trainium across the world.
Buddy, let me know if you can hear me. Awesome. I'm Yang, so I'm a software engineer from the Rufus team. I work on inference optimization. So today I'm excited to share our journey on how we build, optimize, and overcome challenges on our way to scale Rufus to handle large-scale Amazon-scale traffic. So let's dive in. And we are using AWS AI chips all the way. So Rufus is an assistant that can answer customer shopping questions, and then the model that is powered by a large language model trained by Rufus team from scratch. And then the model is also trained using using Amazon's product information and also information across the web. So as you can see from this example, I think it's not showing, but as you can see this example where the customer asks a question on how to choose a board game, then within a second the model will generate a response that have the answer that customer need. And within the response, there's also we also embedded the links and images that can help customer continue explore with Rufus. So since Rufus first launched this year in July, we have successfully supported multiple major events, peak events. So for example, in this year, July, during the Prime Day, we have supported millions of customers shopping with Rufus using a cluster that deployed with more than 80,000 Inferentia and Trainium chips. And then back in this year, in August, we supported an even larger traffic during the Prime Big Deal days, where during the peak hours, we generated 3 million tokens per second. And then during this 2-day event, we also generated 320 billion tokens in total. So when we start to productionize Rufus, and then in order to serve tens of thousands of requests per second using thousands of hosts, we found the Trainium and the Inferentia powered TRN1 Inf2 chip to be our best option, and here are why. So when comparing with, the first reason is when comparing with GPU hosts with similar performance, the TRN1 and Inf2 hosts have better performance with the high-speed cross-chip communication. And then additionally, they also have larger accelerator memories that can enable us to host even larger model in the future. Further, the TRN1 Inf2 host is also very cost efficient, so that and also we can scale them, and they are highly available around the world, so we can scale them and use them to serve customer traffic worldwide. So next, let's take a look at our system architecture. We use AWS ECS to deploy our service, and then with service in each region capable of launching instances using both TRN1 and Inf2, we can scale up the traffic whenever there's a peak burst. And then in the meantime, our service resiliency is also very high because we use cross-region hosting. Within the ECS service in each region, we build and deploy containers that include Triton server powered by VeloM and AWS Neo SDK. This setup best positions us to be leveraging the optimization coming from VeloM and Neo SDK together. In the meantime, we can also leverage and get benefit from the abundant inference server functionality available from Triton. So based on the profiling of our first end-to-end results, we found the performance is not optimal. And then in order to achieve a more smooth customer experience, we define a new latency goal, which is quite aggressive, I would say, given our model size. And before I introduce what are the optimizations that help us bridge the gap, I would like to first introduce how LLM inference works in a quick view. So for example, a customer asks a question on what to buy for camping, and then in less than 1 second, the model returns like when camping, you know what to do, using the insights and also there's a recommendation included. So what's happening in the model during this process? On a high level, the LLM inference can be separated into 2 stages, context encoding and decoding. So context encoding involves the model to build context around thousands of input tokens and process them at the same time, before the first token is even generated. And then decoding involves the predicts next token sequentially, where the output token from the previous step is appended to the input to the current step in order to generate next token. And then this process repeats until the stopping criteria is met. So the context encoding requires processing many tokens at the same time, and then they can reuse the model weights. So this process usually compute bounds, meaning it will go faster if we have more compute plots available. Looking at decoding, because we have KV cache that helps us save a lot of intermediate results, it reduces a lot of compute. But we still need to move the model weights around for whenever we generate the token one by one. So for this process, it usually can go faster if we have a larger model bandwidth, larger memory bandwidth. So now let's look at a few critical optimization that help Rufus to speed up. First is streaming. So instead of returning the token at the very end, once they are all generated, we return them right after each of them is generated. So comparing with the returning all of them at once at the very end, the overall first response latency was reduced from 3 to 15 seconds, depending on the response length, down to 1 second. In addition, the streamed response is also smartly aggregated with links and image previews that inserted into the response that can enable customer to continue shop and engage with Rufus. Another optimization we enabled is called multi-prompt. So for example, we previously used one prompt to ask the model to say, hey, not only generate the white response, which is highlighted here, but also the related question, which is the blue pill, is highlighted there. And then with multi-prompt, we break the prompt into initial prompt and set of follow-up prompts. So using this with this process, the initial prompt have less tokens, therefore the context encoding process becomes faster. So further, by only inserting the follow-up prompt after the response of the initial prompt is generated, we also managed to further improve the model quality because there's better prompt following. Recall that the LLM inference, especially the decoding phase, is bound by the memory bandwidth. So one of the approach to mitigate this issue is to use quantization by compressing the model weights. For example, with a model that have 70 billion parameters, it will usually take around 140 gigabytes to store the model to store the model weights if they are represented in a 16-bit floating point. However, if we quantize them into 8-bit integers, same model weights will only take around half of the size. So with less size, the memory movement, as we mentioned earlier, is also faster. So in case of Rufus, we reduced both context encoding and decoding latency by quantizing our model weights from FP16 to int8, that's the optimization. Besides the optimization I just mentioned, Rufus inference also got continued benefit from the neuron compiler level improvement that are incorporated as each of the official release. And with all this optimization in place, we achieve our latency goal. And all the optimization I mentioned is already available as part of the Neuron SDK as of today. So next, I would like to share our lessons learned when we scale up our service. So first, there are a couple challenges. The first one is, in case of general web applications in today, usually one single host can handle around hundreds or even thousands of requests per second. But when it comes to large language model application, because of the huge compute and the memory that is required, single host only can handle tens or even single-digit requests per second. The second constraint is the end-to-end latency. So in case of Rufus, based on the customer's questions, the response length is different. For example, if the customer asks if this product waterproof, then the response will be shorter, so it will take around 3 seconds. But if a customer asks a more broad question to say, hey, how to buy, what to buy for camping, then the response will have not only that insight, but also additional recommendation to the customer, and it will take a little bit longer time to generate the full thing. So with the variable latency and also the low single host concurrency, distributing the request evenly using the traditional round robin load balancing mechanism does not work well. Because some hosts in this case may be just running very, very hot by crunching through the long request, but some other hosts are just running with very less load. So with this setup, this leads to the overall system availability starting to drop earlier than we thought, without all the hosts within the fleet to be fully utilized. So to overcome this challenge, we leverage least outstanding request algorithms available from the AWS application load balancer. So this algorithm enables us to distribute the request based on how busy each host is. And in case of Rufus, compared with doing load balancing with round robin, this helps improve our overall fleet-wise throughput by 20%. Another optimization that helped Rufus to further improve our throughput, and with the same size of machine, with same size of cluster, is continuous batching. For example, suppose we want to process 5 requests, as shown in this example. So without batching, we have to process them one by one. And then with static patching, the server waits for a certain period of time to accumulate them into a batch in order to process them in parallel. And the batch size is configured as a maximum batch size in advance. For example, if we use maximum batch size 3 in this case, then request 1, 2, 3 will have to get processed first and finished before we can start request 4 and 5. And apparently there's some waiting times which will introduce a lot of some waste of the compute resource. So to further optimize, we use continuous batching, where the server batch sequence at the level of token generation. Now each request can return response whenever it is completed. And for example, as long as request 2 is finished, then we can start inserting request 4 and start processing it. With continuous batching, Rufus team was able to improve our single host throughput by 4x, and this optimization is already available from VLM and the Neuron SDK integration today. So looking ahead, I'm super excited to what's coming next. And then to name a few, we will leverage the new compute functionality available from the Trainium 2 host, for example, the low bit quantization compute and also sparse compute to power our next generation model. In addition, we will also use the Nikki kernel to develop advanced algorithm to help us process hundreds or thousands or millions of tokens with shorter time. And then last but not least, we will continue to contribute to the optimization available using VLM and Neuron SDK. That's all. Thank you so much, and back to Gadi. Thank you.
Thank you very much. Thank you, Yang. We are looking forward to continue working with you and the team to bring performance to all of Amazon customers. Super exciting work. So let's go back to our model, compute needs. We mentioned before Rufus and Yang talked, I mentioned that TRN2 is 30% more compute and more memory than the latest GPU machine. This is certainly very exciting. But what we also realized is that customers come to us and ask for, hey, I want to train a 1 trillion, 2 trillion, even 5 trillion parameter model. We might be leaving some performance on the table. So, and the reason for that is that even the largest instance we can build will not have optimized compute and memory to be able to efficiently train and deploy these monster-sized models. This is where Ultra Server comes into play. Please welcome the Ultra Server. An Ultra Server is essentially 4 TRN2s combined together with high-speed neural link bandwidth to deliver a whopping performance of 80 petaflops of dense compute, over 300 petaflops of sparse compute, 185 terabytes per second of HBM bandwidth, and 6 terabytes of HBM. Essentially, you get 4x of the performance in a high-performance compute node, of course, the highest that is available on AWS. And we are already using those Ultra servers to build Project Rainier together with Anthropic. Project Rainier will have hundreds of thousands of Trainium2 chips working in a single cluster, providing more than 5 exaflops of available compute, which is 5x larger in exaflops than what Anthropic have access to today. This amazing amount of compute will give the Anthropic data scientists and engineers the ability to innovate at an unprecedented scale with the largest model they built to date. We are very, very excited to collaborate with Anthropic on this, and it's coming very soon. But all of this performance and unlocking that amazing performance requires an SDK that simply works and enables maximum performance with code portability and usability in mind. Let's talk about the Neuron SDK. The Neuron SDK supports a wide array of frameworks, libraries, and services. At the bottom of the stack is OpenXLA. OpenXLA is a unified compiler, open source project we co-funded together with Google and Meta to ensure that customers can run their Trainium code and have maximum code portability when they do so. Trainium is also fully supported with popular open source libraries like Hugging Face and PyTorch Lightning and Ray, and as well as observability platforms like Datadog and high-performance inference projects like you heard from the Rufus team, like VLLM, and many, many more. The Neuron SDK software is built from a few major components, namely the compiler, the runtime stack, and the framework integration, plus usability and debuggability tools. You probably heard yesterday from the keynote, the Monday night keynote from Anthropic, that this is the only accelerator they have access to cycle-accurate data when they run their profiling. This is all enabled by the Neuron Profiler. The architecture leverages open standards when possible and supporting performance with distributed training and inference. We'll talk about JAX in length soon, but I want to touch also on some innovation we have implemented since last reInvent on PyTorch. Specifically, the Neuron distributed library, Neuron X distributed, or in short, NXD, for training and inference. Let's start with training. NXD training is an open source PyTorch library that is fully optimized for large-scale model training. It combines ease of use and advanced capabilities for large-scale training with core models for engineering and data science, wide support for all of the training workflows, pre-training, fine-tuning, and techniques, optimization techniques like LoRa and model alignment. And it's all open source built on top of PyTorch. Let's take a look at a quick example of results done by NXD training. We took here a PixArt model, which is an open source model for image generation, and we asked the model to train a blue jay standing on a large basket of rainbow macaroons. Don't ask me why that's the prompt. We thought it's going to be just colorful and nice. Oops, I had some nice animation here that went away. But anyway, what we are showing here is that the image starts with a blur and then, of course, improves as training progresses with a very nice result after the model is fully fine-tuned at the bottom right. Let's talk about NXD inference. Similar to the building blocks we use for training, we have a similar approach for inference with PyTorch with large models. Can be LLMs, can be multimodal models, and can be computer vision models. The library provides performance features like continuous batching, speculative decoding, and also has a model hub for production-ready models like Llama 3.1, 3.2, DBRX, Mixtral, and multimodal models like Lava, all optimized on top of Trainium and Inferentia and ready to go. It's similar to the model training. It has a modular architecture that enables you to bring your own model into NXD inference and reuse all the features quite easily. And of course, an expansive support for training libraries. We mentioned VLLM a couple of times, but also Hugging Face TGI, RayServe, LitServe from PyTorch Lightning, as well as the NVIDIA Triton model serving. We worked really hard on NXD together with the Meta team to ensure that it's user-friendly and straightforward to use. I encourage you all to try it soon. The usability and ease of use is super important for us, so we figured out we tried to think how can we actually improve further usability for our customers. This is where I'm very happy to announce Neuron Expert with Amazon Q Developer. Neuron Expert is a virtual solution architecture at the tip of your hands. It allows you to ask general questions about Neuron and get quick references. Let's see how it works. Here we are asking the model to tell us how to shard models with Neuron. In seconds, you get a detailed answer that has also reference links so you can deepen your knowledge, ask follow-on questions, and engage with Q quite easily. This has been really impactful for us to reduce the load of support, but also allows you guys to run quickly. And this is, again, available today in Q Developer, either on your console or with your favorite code editor. But we wanted to do a bit more. We thought that this is cute, and this will help you guys a lot, but we can do more. Last year, as a reminder, on this stage, I announced Sneaky, our Neuron kernel interface, which allows developers to build performant compute kernels, customized compute kernels directly on top of Trainium. Nikki has two APIs. One of them is called Nikki ISA, which is the low-level access to the instruction set of the chip. You actually can use the chip as a bare metal chip and have full control of all the engines on the chip. That's one option. Another option is more aligned with it's called Nikki language, and it's aligned with the syntax and tile-level semantics that are available today on OpenAI Triton, as well as NumPy. Developers are using Nikki very successfully. You'll hear about it soon from Poolside. But we thought that we can do more to get more folks familiar with Nikki. That's why you can actually generate Nikki code with Q Developer. In this example, a simple prompt asking the model to generate a matmult kernel. The code is, again, generated in seconds, including documentation, including an explanation of what was built. And from that point on, you can copy-paste that into your favorite code editor, VS Code or other, and start your project. This is a fun fact about what you see here. Q Developer, the model behind Q Developer is Anthropic Claude. And we just discussed that Claude is running on Trainium. So this is actually Trainium. What you see here is Trainium generating code for Trainium, which I think is pretty cool. With that, I want to invite Joe from Poolside to talk to you about the work they have done on top of Trainium and Trainium 2. Joe?
Can you all hear me? Cool. So hi everyone, I'm Joe from Poolside, and I just want to give you some context about Poolside and what it is that we do. So Poolside is a frontier AI company that is pursuing AGI by building AI models for software development. Now, that's a very ambitious goal, and from our side, that demands obsession. And in particular, that obsession stretches through everything we do, including the performance of our inference stack. Now, at the moment, our inference stack is primarily based on PyTorch, admittedly mixed in with some Triton and some CUDA to give high performance. The reason why I'm telling you this is because I view us as the typical non-trivial case. We're the case where you have existing code that needs to be ported, there's some things that you need to change, and I just want to talk to you about our experience with that. In particular, though, there's two added things that have made porting for us perhaps slightly more difficult than in your case. So firstly, we are performance obsessed. I'm like a lawyer, I will debate every cycle. And for us, this means that we can't accept any slowdown at all in the speed of our inference. The second thing is that we regularly try out new ideas in our inference stack. And so for us, if we had to re-implement everything multiple times, that would be a non-starter. I do want to stress, though, that even though I've just listed the barriers in the way, it hasn't been a problem in practice when it's actually come to porting things to Neuron. And I want to give you some high-level tips and tricks that we've learned along the way to help you if you decide to make the transition. So, sorry, I should have done that earlier. So the first tip that I want to share with you is that you need to change your mindset. So when we came to port our platform onto Neuron, we essentially took the PyTorch code that we had, copied it over, put it onto Neuron, and then we worked around the Triton and CUDA that we had. Now this mostly worked straight away, which we were quite surprised at, but of course there were some things that we needed to change and fix. And fundamentally for us, that tended to come down to where we were still operating under a different mindset. So we were still thinking about writing code, say, for CUDA. And it's not really quite the same when it comes to writing things for Neuron. I would liken this to learning a new language that is similar to one that you already know, right? For the first little while, you're trying to build understanding, you're stumbling around, but eventually you get to a point where you understand how the system works. And for us, I'd say that that took roughly about a week. It really didn't take us that much time at all once we sat down and got into thinking about it. But of course, as with any language, we learn every day and the process continues. But I do want to point out that it's worth changing your mindset from what you think is fast to what is actually fast when it comes to Neuron. Now, the second tip that I want to give you is to use the tools that you're given. So Gadi just spoke about the Neuron SDK. In this case, in particular, I'm talking about using the libraries that are provided in the Neuron SDK. So NeuronX Distributed and Torch NeuronX. When we came to port our code, as I've already mentioned, we just took our PyTorch and copied it straight over. And after we fixed some things, it worked. But we weren't necessarily getting the performance that we wanted. And completely coincidentally, we switched to use the tracing that's offered by one of those libraries that I mentioned, and we got a 100% speed up across multiple devices. Now, this wasn't something we expected. We were trying to solve something completely different, but it was obviously a performance thing that we took. And I want to point out that by taking advantage of the platform in whatever way you can, you do tend to get more out of the Neuron hardware. In the language analogy from before, this is like using idioms and catchphrases that you've learned from your new language, right? You aren't just doing direct translation, you're picking up things that will help you contextually. Now, this in particular, exploiting the hardware, is about writing code that is actually dedicated for Neuron. So when we started, like I said, we ported over with PyTorch. The PyTorch tracing compiler is superb, by the way. It works most of the time. We rarely run into hard limits that we can't beat. But as a developer, you know that there are situations where you can out-optimize the compiler because you can make assumptions and decisions that it simply cannot. And for us, in this case, we use the Nikki language, which Gadi just mentioned. The important thing there is that you can write things in a Pythonic flavor that takes direct advantage of the underlying hardware. You can specify operations that explicitly use certain engines or use certain hardware features, and you can profile it perfectly with the Neuron profiler. One of the really nice things about Nikki, as I said, is that it's Python-esque, essentially. So you are able to pick it up very quickly if you know Triton or any other Pythonic language. You also don't need any low-level assembly experience. You don't need any deep technical knowledge of like linking or anything like that. You can simply write something that's very familiar and very concise, and it's very, very easy to pick up. One of the nice things about Nikki in particular, and also the Neuron hardware, is that it enables you to express very succinctly ideas that you can't otherwise. So for example, in our case, we've written some specialized kernels for doing the token generation in the inference step. And these are very succinct kernels. They're maybe 50 lines or so, but you can get something like a 100 times speed up in the inference step and a 2 times speed up in the prefill step. So when you're processing the prompt at the beginning. And this is money that's lying on the ground, right? You have to pick it up. I just want to stress that last point again. So something that we've noticed as we've been using this platform is that a great deal many kernels that you'll see are based on this top case here. Right, they're considering matrix operations, which is great. You can process your prompt very, very quickly. But actually, we found that this is not always what you're spending your time doing when you're doing inference. You're actually spending more of your time doing the second type of operation, where you're taking a vector and you're multiplying it by a matrix, or you're adding to a matrix, or so on. I won't go into the technicalities or the details of how we've done this, but we've spent a great deal of time optimizing our kernels for this second case. And just to give you an idea, we're now in the unique position where the attention mechanism in our inference is no longer a bottleneck, which is quite unusual. And this is simply because we've spent so much time tweaking our kernels and adapting them directly to the Neuron hardware with Nikki. But of course, we always like more hardware. And as someone who's been working rather closely with the Annapurna team, we've been able to get early access to Trainium 2. Now, I'll be honest with you, switching to Trainium 2 was quite frankly, a magical experience for us. So we just took the code that we had, we put it on a Trainium 2 box, and we got 50% more performance for free. I didn't change anything. And that's quite, an unusual experience. But there are other nice things about Trainium 2 as well. So firstly, Trainium 2 has 128 neuron cores in each instance, which is 4 times as many as in a Trainium 1 instance. So right off the bat, you can serve 4 times as many copies of your model per instance, which for us was a big win. The second thing that I really like about Trainium 2 is Trainium 2 has support for this thing called virtual cores. So I just said that Trainium 2 has 128 physical neuron cores, but you can group 2 of those at a time into one virtual core from the perspective of your software. And this gives you a couple of advantages. So firstly, it means that you can present more memory to your application. In this case in particular, when you use the virtual core grouping, you get 24 gigabytes of HBM per virtual core, which is more than the 16 gigabytes of HBM per neuron core that's offered in Trainium 1. The second thing, of course, is that you get even more on-device parallelism. Right? You have 2 cores that are processing the same amount of work, which is an amazing use case. Right? As AI applications get larger and there tends to be more and more stuff that's going on, having the ability to churn through all of that input faster is a complete game changer. And even when you do that, even when you group those 2 cores as one virtual core, you still have twice as many instances per box. So you still have 64 virtual cores per box, which is twice as many as on Trainium 1. And for us, this is an unbelievably useful feature and it's something that we look forward to taking advantage of. Now, I just want to show you some performance numbers. I want to stress that these numbers are entirely provisional. We've still got a lot of work left to do in terms of optimization. On the left here, you can see our numbers for Trainium 1. So you can see that at a 2K context length, we get about 26 tokens a second, and that drops down when you come to the 4K length. In the middle there, you have Trainium 2. Now this is just naively ported. We haven't done any optimizations at all for Trainium 2 on that middle set. And you can see that you get that free roughly 50% increase in the 2K length, slightly less in the 4K context length, that's okay. And this last column at the end is the elephant in the room. Now, I've just spent all of this time talking to you about how you can optimize by using 2 cores as one virtual core. But actually, when we profiled our model, we discovered that we weren't actually using both cores fully in every situation that we could. Now, thankfully, Nikki has this nice new feature coming called sharding, which enables you to explicitly say, hey, I've got this input data in this Nikki kernel. I want this core to process this, and I want this core to process this. And of course, this just lets you explicitly specify what parallelism you want and how your data should be processed. And as you can see, this leads to a substantial performance increase even over the regular Trainium 2 code. Admittedly, it drops down a little bit for the 4K context length, but as I've said, this is primarily because we haven't truly finished optimizing yet. And we look forward to continue to optimize this code for Trainium 2. And with that, I'll hand back over to Gadi.
Thank you, Joe. Amazing. Amazing work by the Poolside team, and we are looking forward to continue partnering with you and getting to new performance sites. This is just super exciting for me. So we spoke a lot about PyTorch. Let's change gears and talk about JAX. So today, with the launch of Trainium 2, we actually also announced open source partnership with Google. We are very proud to partner with Google around JAX to enable more use cases and make sure code portability with JAX allows customers to choose the right hardware for their solution. And of course, the JAX native integration of the OpenXLA project, which I mentioned before, makes it really easy. And I hope you'll see that very soon when Matt goes on stage. There are a few other customers that are already using JAX. The Anthropic team that we talked about quite a lot today, they actually started using JAX over a year ago. And they have seen great results in moving and porting their code from the platforms they were using onto Trainium very easily because of the code portability that is built in natively into JAX. And with that, I'm very happy to invite Matt to stage. He's actually the original author of JAX, started as a skunk project within Google, and then grew to the amazing framework it is today. I'm very proud to accept to the stage Matt.
Hey, thanks, Scotty. Yeah. All right. Sound okay? All right. Yeah, so I'm Matt. I work at Google DeepMind, and I'm here to tell you just a little bit about JAX. So this is JAX in one slide. JAX is a Python library for numerical computing and especially large-scale machine learning. You can see on the left an example of JAX code for implementing just a very trivial, fully connected neural network. And you can see it looks just like writing JAX code looks just like writing NumPy code. So behind the scenes, when you write JAX NumPy functions, when you call them, JAX uses the OpenXLA stack and the XLA compiler to run those functions on CPUs, GPUs, TPUs, and now also on Trainium. And so JAX was built from the ground up to use XLA, and being able to run NumPy functions on accelerator hardware this easily would have been a dream for me in grad school, and so I'm glad that it exists now. So that's sort of the first half of JAX, is like, oh, just run NumPy on any accelerator hardware you want. That sounds pretty great already. The second half of JAX, where it really starts to shine, is to do with what we think of as function transformations, these colorful grad, JIT, and VMAP things I've highlighted here. So function transformations are things like grad for autodiff. So if you want to train your network, use autodiff. Grad is our function transformation for doing that. JIT, for just-in-time compilation, is where you can say, I want to stage out this entire function to the compiler. Not just compile individual JAX NumPy functions, but I want to stage out end-to-end the function that I wrote for my neural network prediction function or loss function or optimizer update step. And by staging out to the compiler, not only can the compiler do optimizations like deciding fusions or layout optimizations, but this is also what gives JAX the power to scale from one accelerator chip to many thousands. So people have been able to do a lot of different things with JAX. We've heard about some of them. So as you may know, Google DeepMind's all of the large language model and large multimodal model work is done with JAX. Also other companies like Anthropic and Apple Intelligence, but also like XAI on GPU, they use JAX to power a lot of their large-scale machine learning work. But there's also work on image and video generation from Google, like Imagen and Midjourney, and work from Google DeepMind on mathematical reasoning, these sort of things. So JAX helps power all of these. A bit beyond standard machine learning, JAX also helps power a lot of scientific computing. So for example, AlphaFold 3 for protein prediction and Nobel Prize generation. It's also used in robotics for things like simulation on accelerators, and for things like climate modeling, large-scale climate modeling. And finally, JAX is used all over in academic research, from synthetic biology to astronomy to things like cutting-edge AI research. So how exactly does JAX help all these people, and how does it power all these things? It really comes down to that JAX gives you AGI. And by that I mean a simple composable functional API paired with the fact that it's geared towards compilation and scaling up just from the beginning, and inherent portability across all of these platforms. And to try to show you some of those things and give you a concrete taste, I'm going to attempt a live demo. Let's see if we can pull this off. All right, hey. Great, so this is a Trainium instance. It's Trainium 1 because I prepared this before this morning, but I'm excited to try this on Trainium 2. Let's just, I started this notebook. Let's just start running NumPy operations. So here we've imported JAX NumPy, and we're making a big matrix and multiplying it together and printing out some results. That's great. And you might not even know that this is running behind the scenes on a Trainium chip. But if you look, you can see that yes, the data indeed live on Trainium neuron core here. And just using these kinds of operations, like these NumPy operations, we can start to write neural networks. So here's our toy neural network from our first slide, along with some parameter initialization code and just some synthetic random data. And we can start to run it. We can say, let's run a prediction step. Let's evaluate our loss function. So that's just running JAX NumPy on Neuron or any other platform you want. If you want to start to stage things out to really start to get performance, you can use jax.jit. That's our decorator for just-in-time compilation. You apply it to a Python callable, it gives you a new Python callable that is end-to-end stage out, the entire thing, sort of whole graph capture if you like. So here we're running our prediction function and our loss function, and up to floating point tolerances, you can see we're computing the same numerical function, but now it's been staged out. Where JIT really starts to shine is when we do parallelization through automatic partitioning of computation. Let's take a look at that. So we were actually just running computations on one neuron core, but that's not making good use of this machine that I have running because we have 32 neuron cores available. And moreover, when you're running, you might want to scale out to hundreds or thousands of chips. So let's look at how JAX has one unified approach to expressing batch data parallelism as well as any other kind of parallelism you might like. So here's a simple batch data parallelism example. We're going to take our devices and we're going to say, let's make a mesh out of them. In this case, we're going to start with just a simple one-dimensional mesh of our 32 devices. And we're going to call that mesh of devices in a line. We're going to say, let's name that single axis the batch axis. And then we're just going to put our data, our inputs and our targets. You can think of this, our data is two-dimensional, right? And the batch axis is the leading axis. And so we're saying, take a chunk of inputs, a chunk along our batch, and give each chunk to one of these neuron cores. So this is just a simple visualization of our 2D array of data. And even though it appears like one array to JAX, we can see that it's backed by memory across all these different devices. We've given one chunk of that data to each of these different neuron cores. And now we can do the same thing we did before. We can compute the loss function, and we can run predictions. And this is actually being parallelized for us behind the scenes. In this case, the parallelization is really simple, just batch data parallelism. But it's just happening behind the scenes with the compiler. It has to recompile for every new sharding, of course. And we can see, in this case, this is just simple batch data parallel case. Indeed, our predictions are coming out laid out in a parallel manner as well. That's just giving you some indication that indeed we are keeping the data distributed and partitioning the computation to be parallel. Let's start mixing that in with more. So here we're going to use jax.grad for autodiff to just do some training of our toy neural network. So you apply jax.grad to the loss function. That gives you a new function that computes the gradients with respect to the first argument. So if we run this, remember this is running in batch data parallel because we just made our data distributed. And you can see we get gradients out. If you think about it, actually, the compiler is doing something non-trivial here because to get the gradients, it has to automatically insert an allreduce to compute these results. But we don't have to worry about that. We just get to set the sharding, and it's being parallelized automatically for us. So here's a simple update step. This is simple gradient descent on our parameters. We can see we're doing grad underneath our JIT, and we're just going to loop calling this many times. So this whole update step is being sent to the compiler. It can be end-to-end optimized, and we can see that now this is going to be, loss goes down. That's great. Maybe we can have a bigger step size. After all, loss keeps going down. That's great. That's AI. So I think I might skip this section. But briefly, you can even compose more JAX transformations together. This really starts to give you a lot of expressive power. In this case, we can use VMAP, which does efficient vectorized batching of computations to do things like compute per example gradients. So if you're doing some computations, for example, at differential privacy, maybe you want per example gradients, JAX makes that super easy to express. And of course, you can compose that with autodiff and with end-to-end just-in-time compilation and automatic parallelization. So as one final example, I'll just show how we can try different parallelization strategies. So in this case, we're going to take our mesh of 32 devices, and we're going to make it two-dimensional. We're going to say, I actually want to do some model parallelism, some tensor parallelism, and also do some batch data parallelism at the same time. So we're going to take our 32 devices, we're going to think of it as a 16 by 2 mesh, and then we're going to place our data so that our inputs, our input data is sharded along its batch dimension and along its feature dimension, and the input parameters are also sharded along their sort of leading feature dimension in this way. And I'm going to make one change to our example code as well, just as a hint to the compiler to say how we want to keep things sharded. I'm going to annotate this intermediate with a sharding constraint to say I want the results of my matmls to stay sharded in this way, where I'm doing both batch data parallelism and tensor parallelism. And with that change behind the scenes, let's see what our loss value was before, 415,339 something, and now, now we're getting this result out. Now instead of just batch data parallelism, we're doing batch and model parallelism. So that's how JAX gives us one unified mechanism to do parallelism and to scale out from one chip to 32 cores in that case to many thousands. So that was just a brief introduction on JAX and why it might be useful to you. And I think with that, I'll end and hand it back to Gadi.
Thank you very much, Matt. This was awesome. You guys, there is a test on the way out, just to make sure you got everything here. This was pretty awesome. I think the main point is that the code is portable. If you are running on Trainium, you use the same code. If you run on GPU, it will be the same code. Of course, different sharding dimensions because you have 8 GPUs in an instance, you have 16 Trainiums in a Trainium 2 instance, and things of that nature. But largely, the code is portable, which is awesome to see. Thank you, Matt. And last thing I want to talk about, JAX is going to be very impactful for the customers I mentioned, Anthropic and Apple and hopefully many other customers that will adopt JAX. I want to thank all of our Trainium 2 launch customers and partners. Wouldn't be able to continue and develop Trainium, Neuron, and this amazing technology without our wonderful customers and partners, making sure it's easy to use and adopt, and evolving over time to more performance and more scale. So huge thank you to all of our customers and partners. Last thing I want to highlight to you guys, there are a lot of sessions this year around Trainium and Inferentia. These are it's a bit of a shout out to the rest of the team that is working really hard at reInvent. We have more than 30 sessions this week for you. This is only part of them, so please scan the QR code. You'll get the full list, including hands-on sessions on Trainium and Inferentia. I wish you guys, thank you for coming. I wish you all a great reInvent, and see you soon. Thank you.